In this video, I'm going to walk you through using the serial plotter. This is just a basic introduction to the plotter. There are going to be a couple other videos where we walk through the details to get the most value out of it. I find it an incredibly valuable tool to get a first view of the data coming in from an A to D, for example. And so to do that, I'm going to set up a simple sketch in order to measure data from an A to D. Now the serial plotter is basically going to take data that is being printed over the serial link to the serial monitor, but instead of displaying it as numbers one after the other, it's going to plot it in real time on the serial plotter. And then we'll walk through what it looks like. So to do that, I'm going to use a function in order to take data from the ADC channel 1 and then print it to the serial link, and then we'll look at it with the monitor and then the plotter. So to start that, I'm going to grab a new tab. This function I'm going to call, the tab I'm going to label as take data, and it's going to be really simple. And so the first line is measure from ADC channel 1, and that's what we're going to do. So we're going to start out just really simple. We're going to use the global variables that we've already created in the main sketch. And we're literally going to take a measurement from the ADC. So this is going to be the voltage measured by ADC channel 1 in ADU is going to be equal to the analog read of, let's see, this is going to be channel 1, and that's it. And then we're going to convert that. So this is the voltage on ADC channel 1 in volts is the value in ADC channel 1 in ADU divided by the full scale 4095, and I'm going to make it a floating point number so that we get more accuracy on it, and otherwise it would be 0 to 1, and this way we'll have a fraction times the voltage that's on the DAC as the reference in volts. And you see, if you use self-documenting variables, then it's easy to remember, and they literally write themselves. Let's see. Oh, and we need at the very beginning to call this a function. So it's void. This is going to be function take data. Nothing is passed other than through the global variables, and we set this up as a function, and then this will move to the end. Okay, let's see. So we're going to take the data, we're going to turn it into a voltage here, and now we're going to print it out. And so we have a serial dot print. This is only one at a time, so we're going to do a line feed, and this is going to be the voltage on the ADC one. This is going to be in volts. And we've seen before, to get millivolt values, we'll use 3 digits over here, and we're done. And this is it. So let's clean this up, and we'll shorten it up a little bit. This is all we need to take data and print it to the serial port. We're going to do this over and over again. And of course, we need to call this from the main program. So we copy this. We go to the main program, and now you begin to see what the main programs are supposed to look like. A few commands, but mostly function calls. And this is it. And of course, we'll clean this one up as well. And now, when we run it, we're going to take data from the ADC. I have going in just a DC voltage, and we'll move that around. And let's see what we get. So we upload the sketch. We're compiling, uploading. And now sometimes you'll notice, and this is a good example, that hey, we're hung up on the uploading. 9 times out of 10, that's because the COM port is still open, and it's messing up the communication. So I'm going to close that COM port, and we'll do it again. And usually the next time we get an error, can't find the port because there's information clogging the serial channel, and then we upload it one more, and now the serial channel is unclogged, stopped, and now we upload again, and it usually works. So that is one small complication. You got to watch out for it. But it's easily fixed. And there we've successfully uploaded. Done uploading. And now if we look at the serial monitor, we'll see the measurements coming in. And I think I have it set for something in the order of about a volt or so. So here's the serial monitor. And sure enough, we're just about 1 volt. And you can see the data's coming in really fast. So now that we see it as numbers coming in, let's plot it. So we grab the serial plotter. And here's what we get. Now, the first problem with the serial plotter is that it only plots with a minimum scale of plus or minus a minimum scale of about 3 units per division, 3 or 4 units per division, and it'll auto scale. And we're looking at a voltage that's 1 volt. There's hardly any resolution at all that I have here. It's not very useful looking at this on the scale. So knowing that there's a limitation in units of 3 units per division as the finest resolution we can have, we want to make sure that any number that we want to plot has a lot of digits in it, so that 3 units per division makes sense and we can see some detail. And I'll show you a little later how we can adjust the scales in our program in order to fix the scales. But for now, I'm going to change the voltage that I have from volts that I'm printing to millivolts. And so I take that value that we're printing, I multiply by 1,000, and again to keep it as a floating point, and now we're going to plot millivolts, and so my scale at the minimum will be 3 millivolts per division. So now let's take a look at what that is. Now I left the COM port open, so it's going to give me an error. Doesn't like trying to upload. Yeah, gave me an error because the COM port was open. So I want to close the COM port. It says close. Now I upload again. So generally the most stable operation is when the COM port is closed when we're uploading. Now we're uploading fine now, and here we go. Okay, done uploading. We know what we're going to see if we look at the monitor. We're going to see all the millivolt values. Here are the millivolt. So we have large numbers, and we can go ahead and plot those to plus and minus or 3 millivolts per division. So we close the serial monitor. Now we open up the serial plotter, and here we go. We're about on the average about at what 25 millivolts per division. You see all the noise. You see the data going by really, really fast. Gosh, it's really hard to make sense of it. We have the combination of the scale changing, and it's going by really fast. And it's important to keep in mind that it's hard to tell as it's going by so fast, but there are 500 individual points plotted at a time. As the 500th point is plotted and the next one comes in, the 501st, everybody's shifted over 1. Really hard to see that. And so to make it easier to see, I'm going to slow down the plotting. And I can do that in a couple different ways. I can literally just add a delay. And let's see, so I have 500 points, and if I send them out at 100 points per second, so I put a delay in here of 10 milliseconds, then they'll come out, let's see, 100 points per second, 500 points. I'll have 5 seconds worth of data plotted. So let's try that, and we'll take a look at that. And again, I need to close my COM port here to get stable uploading. So upload, upload, upload. We're uploading, done uploading, and now let's look at the serial plotter. Okay, and now we can see it's slowing down. We're still getting the data coming in. After the 500th point is plotted, which is basically 5 seconds, now it's scrolling by. So that's one way of slowing the data down, but we're still leaving a lot of information on the table because after all, the data is being taken very quickly and we're just sitting here waiting 10 milliseconds. Terribly inefficient use of the data. However, if I change the output voltage, here I am tweaking the value, you can see that voltage changing in real time. So instead of going ahead and just putting a delay, hey, let's count data for a certain amount of time. And so we're going to establish an averaging time, and we're going to take data as much as we can for that averaging time we select, and then we're going to plot that. And so the way we're going to do that is we're first going to define a new variable, which is the averaging time. So we're going to come over to the main program. We're going to keep that as a global variable, and we're going to call averaging time. Let's see, we'll do it in milliseconds, and we'll keep it as an integer. So it'll be an integer of averaging time in milliseconds. And you know what? Let's do it as a float, in the expectation in the future that we're going to want to make that a very precise value. So we'll do the average time in milliseconds, and for now, let's make that 10.0. That's the averaging time, and then we're going to now we're going to store everything in this value. We're going to take the data, we're going to add it up, we're going to average it, which we've done before, and then we're going to convert it to the value in volts, and we'll display the volts. And so we're going to do that with a while loop, and the while loop will let us take data for a fixed amount of time. And to do that, we need to count how many samples have we taken. So I'm going to create a new variable. It's going to be a long, and it's going to be I of a counter. I think I only have one counter, so we'll just leave it as a counter. Let's see, what else are we going to do? And then we'll set it equal to 0. That's the starting place. We'll create a while loop. What we want to do is take a measurement, add it to the previous one, and keep doing that while our time is less than the averaging time. So I kind of need to know the time right now. And so I'm going to create another variable, I of timer 0 in microseconds. This is going to be the time now. I'm going to make that equal to that's the time now. And then I'm going to start my loop. And I want while the current time is less than the start time plus the averaging time, so we're within the averaging time, I want to keep counting up and averaging the measurements. So the format is while, and if we're not sure, if we don't remember what the format is, remember you click the mouse in the command, right mouse click, you get the contextual menu. We go to Find in References, and here is the information about the while loops. And here's the syntax. While this expression is true, then we're going to execute these statements. So while this relationship is true, we're going to execute these statements. That's the format. So while the current time, which is micro, is less than or equal to the start time, which is I timer 0 in microseconds, plus the averaging time, and that is in units of millisecond. This is where putting the units at the end of the variable is really valuable, because I have to remember, oh, that's in milliseconds, this is microseconds, and so I need to multiply this by 1,000 in order to get averaging time in microseconds. And so this time interval here, this is the start time plus the averaging time. This is when I want to stop. And as long as the current time is less than this, I want to keep averaging. And what do I want to do during this time period? Well, first I want to count how many averages I've taken, or how many measurements I've taken. So I'm going to increment the counter. And so we'll increment the counter. And then I want to take a measurement, and I want to add it to the previous one, because I'm creating a continuous sum. ADC 1 in ADUs. And I already initialize this as a long, so I can store a lot of data in it. That means that before I get into the while loop, in addition to initializing the counter as 0, I need to initialize that variable as 0. So I need to set the voltage of the ADC channel 1 that's in ADUs. I need to set that equal to 0 as well. So we've initialized that to 0. We're going to start counting. This is the first iteration. We take a reading from channel 1, we add it to the previous one, and we continue that process. And when we're done, we're going to end out of the loop over here, and we're going to divide by I counter. And here's where we have to be a little tricky, because I counter is an integer, and when I divide it, I want to maintain floating point value. So I'm going to divide it by I counter times 1.0, and that just turns it into a floating point number. And so this is the average value in ADU, and of course I'm going to scale that by divide that by the number of ADU full scale multiplied by that value. And so this is now the voltage in volts. Now it would be nice to know how many data points are we actually taking. So before we do the serial plotter, let's just print out the number of terms that that we're averaging. So we're going to add here a serial dot print of I counter, and remember, we want to space them with a little space between them, and so I'm just going to print out a little space here. Serial dot print of little space, and then we'll print the value that we get in millivolts. And then we don't need the delay, and we're done. And now again, let's auto format it. So here's what we're going to do. We're initializing these three terms. We're setting the counter to 0. We're setting the ADC value to 0 that we're going to contain or store the running sum. And we're going to start the timer and say, start the time now, record the current time. And while the current time is less than that start time plus the averaging time in microseconds, this is all in microseconds, while that's the case, keep doing this loop. Increment the counter and take another reading from the ADC channel 1, add it to the previous one, and keep going. And when we're done, we're going to come out of the loop, and we're going to have this many points. We're going to average them, we're going to scale them, and we're going to print out the counter values and the ADC values. And so we're going to do that. We are already set for the averaging time here in milliseconds for 10 milliseconds. And then after we look at the number of points, then we'll look at the plot. Okay, we're ready to go. Let's upload. So, up, and I left the COM port open, so we're probably going to have an upload error. Yep, there's our upload error. The COM port's closed, so let's do it again. And we're upload. Looking good. And we're uploading. So now let's look at the serial printer and see, or the monitor. So, you know, in 10 milliseconds, we're taking 351 points, and here's the value that we're getting. That's great. Now that I know 351 points, we're not leaving data on the table. We're still taking every 10 milliseconds, we're taking a result, but we're using all that data that's sitting there. So let's close this out. I'm going to now change the print. I don't need that anymore. We'll just comment it out. And now we're going to print the voltage in millivolts out to the serial link. We can look at it with the monitor, and we can look at it with the plotter. So let's go. So we're going to upload. There we go. And we're done. Let's look at it with the serial monitor first. Look, see our millivolt values. Here it is, coming out roughly every 10 milliseconds, 100 times a second. There we go, looking good. And now let's go to the serial plotter. And there is our measurement. Now, I lied a little bit. I said that I've got a DC voltage. Well, there's also a really small AC voltage on top of it, and oh my gosh, we can actually pick that out. Look at the scale here. Remember, it's 3 units per division is the smallest I can go. And remember, what are we plotting here? This is millivolts. And so we have 3 millivolts per division, and the peak-to-peak value here is roughly about 3 millivolts, peak to peak. And we're able to see that buried in the noise by averaging a little bit. And if I go ahead and I change the DC value, here I've just popped it up, and we're auto-scaling again. So we're slowing it down, we're adjusting the time base, we're taking data, we're displaying it at about 100 points per second, 10 milliseconds between points. Got 500 points full scale. That means we're looking at snapshots of 5 seconds altogether. If I increase the averaging time, that will slow down the rate at which we're sending data. If I make it not 10 but 20 milliseconds as an averaging time, then we'll have not 5 but 10 seconds full scale. So let's do that. Again, we want to close the serial port. We're going to go in here, we're going to change this to 20 milliseconds per point. So we're going to be averaging over that 20 milliseconds. We're not throwing data away, we're using it, we're averaging it. And then we're going to be plotting 500 points at 20 milliseconds each. That's 10 seconds full scale. And so we have to re-upload. Hadn't closed the serial port there fast enough. And so now we're going to see 10 seconds full scale. And let's go to our serial monitor. There's the data coming out. And let's go to the serial plotter. And here we go. And now we're at 10 seconds full scale. And so you can see we have to fill the 500 points. After the 500 points are filled, then we start scrolling, and at any instant of time we see the last 10 seconds worth of data. It's a great way of monitoring what we've got. We don't want to use a delay statement to control the horizontal scale. We want to use an averaging statement to control the horizontal scale. That way we're not throwing data away, and we're getting a chance to see what that data looks like. And the more averaging we do, we can decrease the noise as well, and you kind of see that here. And of course, if I change the offset, here we go, changing the offset a little bit, it auto scales. And in the next video we'll talk about how to maintain the scales automatically. So this first video we've looked at how to change and adjust the time base, and we do that by averaging the data as it's coming in and then displaying the average point, and that controls the total time full scale. In the next video we'll look at how do we adjust the vertical scale.